Adsorption isotherm. We all know what adsorption is now. The extent of adsorption on a surface generally depends on the nature of the adsorbent and the molecules of the absorbent, and is function of its pressure or concentration and temperature. So a plot between the amount of the adsorbate substance absorbed and the pressure or concentration will be taken, and of the adsorbate at constant temperature called an adsorption isotherm will be formed. Now these are possible. There are though 5 possible graphs that can be drawn, but in this case I have shown 3, in which this one is showing chemo absorption, these are physical adsorption. So we have these graphs. Now this one, type 1 isotherm, actually all these are drawn taking amount of substance adsorbed and pressure. Now in type 1 isotherm, this is chemoabsorption. So as chemoabsorption, the amount of gas absorbed per unit mass of the adsorbent increases linearly. We have seen from this extent this is increasing linearly, and then this is going to become almost stable over here. Now consider this diagram. This picture is showing solid adsorbent on which a gas adsorbent is coming. It is going to attach to the surface, this free surface. So initially, when there was no attachment of these gas molecules over the surface of this adsorbent, there will be linear increase in adsorption. So these particles will attach. As the attachment will keep on going, this will show linearity, but as the space or surface is completely occupied, the incoming molecules will not be having extra surface for attaching, or in that case the graph will form this structure, this shape. At this position, when this is stable, it means the surface has been occupied by the molecules and there is very less chances of attaching these molecules. So we have this constant shape over here. So this can be represented, variation of the amount of adsorption per unit area or per unit mass of the adsorbent with pressure is often represented empirically by an equation of this type, in which y is equal to x by m. X is mass of the gas absorbed and m is mass of the adsorbent. So this ratio will be taken, and it can further changed into this form. So x by m denotes the mass of the gas absorbed per unit mass of the adsorbent. P here is the equilibrium pressure of the gas. K and N are the empirical constants depending upon the nature of the solid, gas and temperature. Now the plot can be drawn according to it. Let's see. So looking at this graph, we can come to 3 different conclusions. At this stage, when there is linearity, we can say in that case n is equal to 1, and that situation arises at low pressure. When the pressure is low, in that case there is linearity. That means x by m is equal to k p raised to the power n. And when we have applied high pressure, the slope straightens, it flattens. So in that case we can say the effect of pressure is minimum, so the power is turned out to 0. So we have these two equations, one it is at low pressure and one it at high pressure, whereas in between the moderate pressure the value of P changes by 1 by n when this value n is greater than 1. This equation will be taken. So at low pressures the graph is linearly straight line and sloping, and at high pressures the pressure beyond the saturation pressure 1 by n equal to 0. So we are taking this equation finally, this one intermediate pressure. So this is going to represent our present situation. Let's take it separately. Now this complete curve for any gas, no matter how many curves are there, they indicate that at a fixed pressure there is a decrease in physical adsorption with increase in temperature. These curves always seem to approach saturation at high pressure. This is how they are approaching. So this takes place during high pressure application. Now let's take logarithm of this equation. So it will turn out to be log x by m is equal to, we have log k and then the power of p will be taken 1 by 2, or sorry, in this case we are taking 1 by n. We have n value over here, so this is going to be 1 by n log and this value at base p. So this is Freundlich isotherm, and it can be verified by putting various values log x by m against log k. So let's plot the graph once again for Freundlich isotherm. So we have converted the graph into Freundlich isotherm. Log x by m is taken over here and log p onto this axis. So the validity of Freundlich isotherm can be verified by plotting log x by m and log p. If it comes to be a straight line, as in this case the Freundlich isotherm is valid, otherwise not. The slope of the straight line gives the value of n by n. So this is equal to 1 by n. This is what the slope is showing, and the intercept on the y-axis gives the value of log k. This is log k. We have intercept over here. So Freundlich isotherm explains the behavior of adsorption in an approximate manner. The factor 1 by n can have values between 0 and 1, as we have seen in the previous graph that the value of 1 by n is for pressure having intermediate range, and if pressure was low the value was coming to be n for n equal to 1, and if pressure was high, then in that case n was becoming 0. So when, let's see the situation, when 1 by n is equal to 0, when this situation is going to occur, when it will occur, when we have this situation over here. In that case the value of x by m, the value of x by m is not going to change. It is constant. So in this situation, when x by m will not change, it remains constant. That means the adsorption is independent of pressure. No matter how much we are increasing the pressure, the value of x by m is not changing. So x by m is constant in this case. You can say x by m is constant. This was the situation, and there is no effect of pressure. This occurs when all the surface has been occupied by the gas molecules on the adsorbent, so there is no more structure or space available, so this situation arises. And now another situation, when in this situation consider 1 by n is equal to 1. It can happen only when n is equal to 1. Then 1 by 1 is equal to 1. In that case, where that occurs, that means it shows linearity. In that case, x by m will turn into kp. So we can say x by m is directly proportional to pressure. This is the situation. As the pressure is increasing, so does x by m linearly increasing. Together they are increasing. So the adsorption varies directly with the pressure, we can say that in this situation. So this is how adsorption isotherms work.